I am Katherine Riley. I am the Director of Science for the Argonne Leadership Computing Facility. My predecessor, Paul Messina, as might have come up earlier in the session, earlier in the summer school, was actually the original founder of the training program, and I've been involved from the beginning, and actually involved primarily focused on software productivity, software engineering with Anshu, who is, I will say, actually at this point, completely organizing the session. so she deserves all the credit here. And what's interesting about this session is it's really evolved. This is the 5th year, and while I haven't gotten your answers to questions I'm going to ask you in a few minutes, because I will try to wake you up a little bit, you will notice that the community is sort of changing. And people are a lot more aware of what the concept of software productivity, software engineering, principles, these types of principles are, and how to use them in scientific applications. So my first question to wake people up is, who has actually heard of software productivity as it relates to scientific applications? Okay. And I don't think you count, Mike. And who actually think it matters, right? Like thinks it's important for what they're doing. Okay, awesome. So I will tell you, well, actually, let me ask one more question. Who's heard of the term technical debt? Great. So there's other questions I could ask. I could about like 20 more to sort of take a survey of people. But this was an incredibly large number of people raising their hands. And I would argue that, in the first session, and even the first year, and the second year of the program, we were still talking to people about, no, seriously, version control is important. Let's talk about version control. It's really valuable. And let me explain why. And it's very clear that I think the concept of, not necessarily a prescriptive concept of this is what you have to do to write a code well, is taking hold, but the concept that these are important to your scientific process are taking hold. And that's a little bit about what I'm going to talk about today. And in one of the more boring slides I have, particularly, is probably the most fundamental idea for me that I want you to walk away with, right? That in order to have a good scientific process, you have to have good software practices. And I'll give you a couple concrete examples of that coming forward, right? If you want to trust the science coming out of the simulation work that you are doing or the analysis work that you are doing, you have to trust whatever application code you are using. And if you can't, you shouldn't trust the answers you're getting. In addition to that, good software practices will increase the amount of science that you can do, or engineering. I sort of use science as a blanket term here. But fundamentally, if you have good software practices, the time to your solution, in a lot of different ways one can describe time to solution, is going to increase. You're going to be able to do more because you're going to be fighting against, you're not going to be fighting against your technical debt as much, all right? I encourage questions, by the way. Anyone who knows me, and there are a few people in this room who do know me, know that I can talk and I will talk. I have a really bad cold, and I'm pretty sure even losing my voice won't necessarily stop me from talking. So please interrupt and ask questions. And what I'll comment again in a little bit is that even there's a lot of people in the room who can contribute to this conversation who know a lot and are really passionate about it. As was pointed out to me last night, it is possible that not everybody in this room was alive when the Challenger exploded. Which was sort of interesting to me. I was in 6th grade. I'm 43, sort of to give you a context, right? And this is relevant to sort of if I describe a little bit of my experience with software productivity and writing scientific codes. But between, say, the Challenger, between, honestly, the Y2K bug. The Y2K bug, right, was an engineering flaw that ended up costing almost $1 trillion worldwide to the global economy. The first estimates were sort of moderate, but like as sort of the years went on and people were making a better assessment of the implications and the cost to fix an assumption in applications, right? This was an engineering bug just by assuming that you will represent a year by 2 digits and that would work. And it was pervasive, right? An engineering bug that cost a great deal of money. I switched over, I sort of moved past the Challenger explosion a little bit, not because I didn't think that was relevant, but it's a very famous example of an engineering error that resulted in something really catastrophic, right? It was just an engineering error. It was just not necessarily not everyone understanding the limitations of a particular part of the solid rocket booster, but also a failure in communication between teams. There's other things people talk about in terms of business practices and communicating that were failures there, but fundamentally that was really just an engineering failure and a failure in communication. And frankly, one of my favorites, and I think one of the most directly relevant to complicated scientific codes, right? But that's sort of in the spirit of big, real sort of building a real sort of object, right, is the Mars Climate Orbiter, right? And this was around 99. And this was an orbiter that NASA launched. It was supposed to orbit Mars for a full 2 Earth years, about 1 Mars year. And they lost it. And they lost it because one team wrote in English units and one team wrote in metric units. And they didn't fix that. They didn't realize it, and that was the analysis that NASA finally made. That's why this orbiter was lost. And again, this was just an engineering mistake. And it was an engineering mistake out of teams on on 2 of these certainly, that had really good practices, that had ways of tracking what other teams were doing and communicating and trying to figure out how things interact. And so in part, this is sort of my good morning, let's scare you. Or at least motivate you to think about this, right? You might not think your code is equivalent to the Challenger. You might not think your code is equivalent to the Mars Observer, but I'll give you sort of an analogy in a minute that might give you a sense that actually, if you're thinking about extreme scale science, your code is closer to that than you think in terms of the cost and investment of time and resources that might go into it. So consider these things, right? That even when you have good practices, mistakes happen, and to some degree, software practices are mitigating that risk. There's a little bit of program management that eventually you'll run smack into in your career. But regardless, mitigating risk is important, right? You don't want to do it so far that you don't get anything done and you don't take any risks at all, right? So you don't get anything big done, but mitigating risks is important. So I promised I'd sort of say, well, why you should think about, well, your extreme scale science is maybe a little bit closer to some of these big failures or big science experiments that you might think of. We have this regular conversation with potential users of the Leadership Computing Facility. And I'll step back and just give you 2 pieces of background on what the Leadership Computing Facilities are, just in case you don't know yet. But there's 2 leadership computing facilities, one at Argonne National Lab, one at Oak Ridge National Lab. The goal of these facilities is to deploy the largest machines for open science in the world. And so normally when we deploy a new system, it is a top 1, 2, 3 system in the world. With the reality of supercomputing, you release a machine, 6 months later, somebody else releases the machine, and there's some jockeying for those top 10 positions. But for the most part, our goal when we release a big machine is we're number 1. Currently, I have a picture of Theta up here right now, which is our most recently deployed system. It is not of that scale, right? This is more of an intermediate machine for us. But we're talking about the biggest machines in the world. And when you look at the cost of how much it costs, to build one of these machines, how much it costs to run one of these machines, and you think about the cost of the LHC, that to build the LHC was about $5 billion. A little bit less, actually. Now that's, though, averaged over at least a 20-year lifespan for the LHC, at least. The LHC is a particular extreme example, but when you actually average these out and you average some of the other costs of running out, it's not crazy bigger than the cost of using a leadership computing facility, doing an experiment on the LHC compared to using a leadership computing facility. And certainly, if you think of other experimental resources, large experimental resources that the United States builds, like light sources, right? There's a lot of light sources through the Department of Energy where people can go and do imaging, and you compete for time to get access to that light source, and you build your experiment at a particular place, and then you run it, right? And the pressure there is really high, and people sort of consider the cost of that experiment very intently to sort of make sure they don't waste it. And it's something actually we collaborate with users of light sources to make sure that they don't, right? Coupling computing so they make the most out of, say, the 24-hour shot that they have. Why am I going down a path of talking about light sources and accelerators? Because people often overestimate or overvalue an experiment compared to a simulation resource. They think it's a computer. And I'm getting maybe the cycles for free. At a leadership computing facility, you compete for time. It's, you are given time if you're successful in that competition. But we give what will eventually be one of the biggest machines in the world, hopefully the country's first exascale machine. We're going to give time to 30 projects on a machine that's going to cost a lot of money. And so while it's not all about money, these are an important thing to keep in mind, that software productivity, on trusting your scientific results, knowing that when you get the shot to run, that you're going to do what you think is about the right thing, having the confidence is really important. Having the confidence in your application and the question you're asking is really important. Now, I'm not going to talk as much today in this talk about, say, making sure you trust the science question you're asking, and that is an absolutely huge question. There are some topics later today that will touch on that. in some respect, there's even just the question of making sure that if you think your code says 1 + 1 = 2, that your code actually says 1 + 1 = 2. Don't assume it. And to some degree, you could boil it all today down to don't assume your code says 2, check that your code says 2. Okay? All right. And I want to point out an example. Now, there are some more dramatic examples I know I'm going to talk about, but I'll tell you that this example has intimate relationships with people in the room who contributed and are mostly responsible for driving this. So we feel comfortable talking about this because many times people aren't necessarily comfortable with their mistakes being broadcast out. But when they're your own mistakes, you're a little bit more comfortable talking about it. So the reality is you don't have control every single moment. You don't get to always have 6 months to prepare for a run, a big campaign that you might have planned. You don't always have that. Instead, what you need to do is, react when somebody says, hey, there's a chance to do something really cool. Thankfully, this model is not as pervasive as it was several years ago. Actually, one of the reasons the Leadership Computing Facilities were founded was because in order for open science to get access to huge resources, it was actually a really big battle, and you would end up in collaboration with machines at, say, in the NNSA, which is sort of the weapons part of the Department of Energy. And they'd say, hey, this machine's going to go behind the fence in a little bit, but you have a chance at a really big shot. Would you like to try to do that? And you have a month to prepare. This actually happened. And there's a really exciting run that, a really exciting question people have. But without some sort of software process, right, to go forward and get people to collaborate and actually make sure you can successfully execute that run, mistakes happen. In this case, even with a software process, a really strict software process, actually, really, and a lot of people who valued software process, a mistake happened. And primarily, a mistake happened a month of prep, a week-and-a-half long run on a Blue Gene. Now, basically, at that point in 2005, it was one of the biggest machines in the world. There was a serious flaw that took 6 months to get to the results, right, after you did the run, because there was basically a round-off error and you couldn't properly track the physics of one particular part. That was the new part that was being developed. So even with a software process, mistakes happen. I want to point that out, why I think that's relevant, why I start with sort of a bunch of examples of stuff will happen no matter what you do, is to understand that walking into today, we're not going to prescribe to you exactly what you need to do. We're not going to give you a checklist that says you have to do it this way. Because the reality is that we could. We could give you a checklist, but it might not apply. In the scientific community, there's a lot of different constraints. And they are not the same as writing code at Google or writing code at Amazon. And often, the biggest one is how many people do you have? How much funding do you have? They're very coupled. very, very, very rarely uncoupled, right? And how much time do you have? And what's the expertise of the people who are developing your code? And what resources do you have actually to do some of these things? You won't get it perfect. You do the best you can. You find the best process that you can implement, and you move forward. And you have to understand that part of the job is mitigating that risk and understanding that even some of the best people in the world, even some of the most senior scientists in their field, have had really big screw-ups, frankly. Have had to retract papers from problems that they've discovered because in the end their code did not say that 2 was the result of 1 + 1. All right. So this is primarily the goal of today, right, is we want to bring forward topics you already know about, right? In some of them cases you will know about, right? Everybody sort of nodded when I said version control, right? But there's a lot of good best practices we can talk about and interesting practices, new ideas about ways you can use version control, new ways you can use unit testing, or not necessarily new ways, but new ways for you to think about how you might use unit testing or deploy that, et cetera, these concepts within your talk, within your project. And so I want you to consider that and not necessarily look at this and go, well, this is a Git talk, I know how to use Git. Look at that and sort of explore what is in front of you and sort of new ways that you could use it. And the reason I say that is the people who are going to be talking to you today and some other people in the room are some of the most experienced people doing software engineering for scientific applications. The Department of Energy has a long history of this, right? It is not something that they're just sort of excited about today, but it's getting more traction in the open community. there is a long history of evaluating how people write scientific applications, what works, what doesn't work. And the people talking to you today are some of the most passionate about it, some of the most experienced about it, have real world experience. This isn't like they've just gone away and sort of studied the sociological issue of it. They've done it a lot over their career. So poke them and ask targeted questions, right? It's an absolutely awesome set of people talking to you today. And frankly, if you have those challenging problems, you're sitting there going, well, how on earth am I going to unit test my, my multi-physics application, which has got more science in it than I even know yet because I'm learning it. How do I bring that forward? There are good ways to start talking about that and some good first steps that you can start doing. All right. Okay, so shifting gears a little bit, I want to talk about how we normally write code. and this is how I sort of started with writing code originally, right? And that's the heroic programming model. Scientists are infamous for doing this. We are not the only ones who do this, but we are infamous for doing this. And really, the concept is that, well, I mean, I won't directly read it. I have issues with reading slides. I won't do that. But it is not necessarily a good thing. And it's the concept, right, that because of some failure in the process, and it may not because somebody did something wrong, just a failure in the process, like maybe you don't have the money to do any other way, or maybe you don't have the time to do it any other way, like, hey, you've been given a month to do a really cool, huge simulation, so you have to go fast. Because of some failure in the process, you have sort of left behind practices that you might otherwise be considering, or that you should be considering. And it's often one person or two people, it's the canonical thing. You're trapped in a room and you're banging out code hard one evening, right, to try to get the work done. And what's important to understand is that science teams often do this, and few people historically have really seen problems with doing it this way. As I said, I think one of the most exciting things is that more and more people are understanding the value of this. And I'll even talk further about some of the challenges there, right? That whether your career is advanced doing software engineering might be a genuine question, but more and more people are seeing the value of this and the importance of it, especially in terms of trusting the science results that they get. But many don't see a problem. And so it is very likely, right, especially perhaps with people from previous generations, that you will walk in and people will go, well, I'm doing it this way. This is the way we've been doing it. I'm not going to implement an X because I've never done that before and I've always trusted my science. Understand that is likely to happen at some point. But I want to make sure that you have the concept of heroic programming so you can understand how that contrasts to sort of a well laid out plan, right? How that compares to having a process, and in the happy place of knowing that, hey, I want to run this simulation and I'm going to spend the next year trying to work on the development to get there or something like that, and having a plan to execute it. So what's wrong with heroic programming, right? Fundamentally, I'm just going to skip straight ahead through this, is that it worked. I would say this even worked when I got started. So I got started about 23 years ago. It depends on, I'm not exactly sure when I got started, but somewhere around the late 90s, right? I think there were still situations where you could do that. There were scientific questions where you could have a grad student go away and just sort of completely rehash a piece of code over the weekend, and maybe it would work out okay, maybe. The problem is the questions that people are asking are getting more complex, right? Science moves forward. It can occasionally move back when it's like, all right, let me go actually re-ask that really basic question again because we have better understanding. Maybe we'll get a different answer. But for the most part, we have a better scientific understanding, so our codes are more complex. I don't have conversations with people saying, I had this multi-physics code, but I don't really need to do that. I just want to go back and study this really simple Leonard-Jones potential on this same problem, right? Because that's what I want to do right now. Everybody's going and saying, well, I have this really complicated problem. I have length scales of trying to understand how a city operates, right? And I'm trying to understand everything from how weather is impacted in the city to how a car is moving, and how do I get all of those length scales, and how do I get all of that physics interacting? Those are the types of problems people are coming forward with today, not something simple, not very rarely sort of a single physics problem to tackle. When you have this more complex scientific question, you have more complex scientific software, and as a result, you've got areas of very different expertise, right? An applied mathematician is an applied mathematician, right? There's a reason that they're doing that. They're studying how to take a particular numerical model, right? A mathematical model, and turn that into numerics that make sense, that will actually give you the scientific result you want. Now, some people can do that, right? You might go away and read a few papers or sit down with an applied mathematician to understand what you really need to implement. But if you really want to advance, these are very different aspects these are very different areas of expertise. Performance is one that people actually don't often think about in regard to this too, right? If you want your time to solution to be fast, because you can ask better questions if your time to solution is fast, right? Just think of it like writing a letter, right? If you can ask a question and get an answer in a day versus ask a question and get a letter in 6 months, you're going to ask better questions. At least most people operate that way. So the performance of your application, everything from how you've structured your data all the way through maybe how your loops are running on the machine. There's whole people whose careers are based on doing this, right, and understanding how to do it. Can somebody tackle and sort of do their best on these? Yes, but it gets harder as the codes get more complex. All right, and so one of the premises we want you to walk away with is that it's not easy, certainly, for an individual to do all of these things. And fundamentally today, when we see an individual who is trying to do these things, they're doing, I hope, the right thing, right? Where they're saying, well, look, to implement a numerical solver that I need, I'm trying to use a library, because otherwise I'm going to go away and spend 2 years trying to develop the solver capabilities I need to solve my science. All right. And so this touches back on the exact same points, right? In extreme scale science, it's not just that your science understanding is bigger and you have more complex questions to ask. You've got extra stuff. even on mid-scale science, right? Like you're trying to use a pretty reasonably large-scale cluster, right? Things get more complicated in your application. And basically, the root of that is that you've got these more complex codes, a lot more moving parts, trying to move onto a machine that's moving really fast, or machines that are moving really fast. If there is one thing that has been consistent in my career, is that I don't sit down on a machine and run on it for 5 years. Even though we have about a 5-year lifespan at the facility for a big machine we put down. Even before I got there, it was normally like 2 or 3 years, and then I'm looking at the next one. But 2 or 3 years, if you're doing some deep development, is about the lifetime to do some deep development. And so with this incredible speed of change, of heterogeneity in systems, but also heterogeneity in the larger computing environment, the ecosystem, as we often call it, you have to have a code that's dexterous. You have to have a code where you do have separation of concerns, where basically what that means is where you can say, well, I'm running on a many-core architecture right now that has this many threads on a node. I'm going to run on one in a year that looks like that. And I know that memory models are doing something crazy, so maybe I can find ways to abstract my data structures, right? That can give me a little bit more flexibility. But without those, I can tell you from experience that you end up rewriting huge chunks of your code every single time a new machine comes. And that's not fun. And in the spirit of probably being a scientist and want to getting to your results, and actually ask your questions and advancing, even just advancing perhaps the application, you want those things ready, and you want them ready fast. You don't want to be spending 2 years adapting an application. I would like to say that, the ecosystem will be improving and not changing quickly. But as I was talking about before this talk, I will say that while I thought things were changing over parts of my career and sort of slowly accelerating, some like in the past 7 or 8 years, yeah, the ramp's gone way up now. Things are going to be accelerating and changing even faster. So not just the things that will happen on the extreme scale systems, but what will likely even be on your university clusters are going to be changing fast. So you want a code that can be dexterous, right? That can use different architectures, that can use big changes effectively. All right, so I asked earlier who knew the concept of technical debt, and a few people raised their hands. And this is directly tied to what I was talking about previously, which is that technical debt is really the consequences of the choices you've made in what you're doing with your application. If you have decided to, the most extreme example, to write all of your solvers in assembly, you have a pretty big technical debt if you move to another machine that doesn't use the same assembly or doesn't have the exact same instruction set, right? You have a big technical debt because you have to go back and rewrite all your solvers for whatever machine you're going to. But you can pull that up higher. The assembly is sort of a traditional example, right? But that can go higher. And it's basically the consequences of poor choices or the consequences of choices made at the moment for whatever reasons, right? Like because you didn't have the resources or even sometimes the knowledge, right? You didn't know to make a different choice. It's still technical debt. It's not necessarily a bad thing, but you have to understand that any application will have some degree of technical debt. You will. If you manage to write a code with no technical debt that's totally dexterous and it's got performance, write a lot of papers about it because we'll all be very interested, okay? So there will be consequences. And frankly, there's other consequences to this besides just how fast you get to your solution. Technical debt for a scientific application that has not done reasonable validation of their results might be that you publish papers that are wrong, and you have to go back and retract those papers. Right? If you don't have a solid process for verification, that's like the 1 + 1 = 2, and validation that it's actually doing the science you think it's doing, there can be a serious consequence to that, right, in terms of what science you're producing. So fundamentally, technical debt's a valuable one to keep in mind to understand that you can make an informed choice. You might need to make the choice that this is actually going to incur some debt, but I've got to do it right now. Sometimes I/O is a good example sometimes where you have to do that. I/O is infamous for not being particularly portable from one machine to another if you want good performance. And so you might make a choice in terms of implementing an I/O strategy on one machine, changing your I/O strategy, I should say, to use one machine effectively, knowing that when you go to a new file system in a new machine, it might not work very effectively. But currently you're using that one, and you need your I/O not to take 5 hours. So that would be a good example of a very informed, good choice of technical debt. All right. Okay. This is a quick comment about a reality check on all of these things, and to point out that everybody talking today and everybody involved in this track understands something, which is that we get that if you are a scientist, your advancement, perhaps, to professorship, your advancement in your career is not always assessed by how good your software engineering practices are. It looks a lot better, again, than it did 10 years ago, but it is still absolutely true. Universities don't look at your code product, right, and say, well, that's awesome. You're an awesome physicist, right? You wrote this application that thousands of people are using. That's great. They look and go, well, where are your publications, right? Where are your papers? We get that there's a disconnect there, and this is one of the reasons, right, why we're not standing up and saying to you that you have to implement this checklist, right, and you have to make informed choices about what debt you want to incur, what things you can do at the time, what you can do that's best at that particular moment, okay? I honestly do believe there's some advancement. In academia, that's harder. The labs, I think, have a better culture of doing that, although not perfect. But it's a slow movement forward. Even universities, I never thought would engage in a conversation about whether it's valuable to have people who understand the code really well, that code products themselves are a valuable contribution to sort of the intellectual exercise, are beginning to have that conversation, and that blows my mind, right? Some don't surprise me. Some that are actually willing to have that conversation now are absolutely astonishing. All right. I think I touched on a lot of these because I tend to riff a little bit on what I'm talking through. But there are real challenges developing a scientific application. And this is sort of in the same vein that we understand you are not, that you can't do everything. You're not working at Google with a huge amount of money to do perfect software engineering practices. But one of the things to think about is that on some applications, everything's research, not just the science question you're asking. It could be that you're even trying to use physical models or numerics, right? That they themselves are under research, right? A lot of moving parts are involved in scientific applications, right? Especially if you're really trying to push the edge and sort of really trying to push the edge of what modeling and what problems you're trying to solve. And I think that is a particularly valuable one that I want you guys to think about, which is that a lot of these things are under research. And even sometimes what people think of as almost the more base level, sort of the infrastructure of your application might even be research. There's a lot of research that goes into I/O. I want to go back to that example. As I said, a lot of my life was sucked up into I/O in previous incarnations. But there's a lot of research on the best ways to do I/O out of applications. There's a lot of research on just the infrastructure, on how to build a machine with a good I/O system, right, that applications can use. That's another good example, right? You might not think of that immediately because it's not the specific science question you're asking, but it's real, right? And it's a real question that we're trying to solve. One of the reasons it's a research project is because every single time we build a bigger machine, every single time we're thinking about, well, wow, we need to serve now 100 petabytes of data, right, to make sure that we can move the science forward. We're pushing that hardware as much as we're pushing the compute hardware, right? It's not just compute hardware that's sort of advancing and changing. You build a really complex, huge file system, that's its own. In some regards, you can sort of think about that as its own sort of supercomputer, right? Its own super data storage center. And there's also real sociological challenges, right? So one of the biggest ones is that, and this might be getting a little bit better, is getting different parts of a group to talk well. I think there are definitely some people in science who have good communication skills and who are willing to listen. I would not say it is the strong point of scientists. that we want to listen to what somebody else is saying, and we want to listen to their solution and adjust. And if you're working on a big application, you gotta do that, right? Or if you want to use someone's library, right, to move forward, you kind of gotta do that. I think the reality is you'll run into this with anything you do in your life that nobody really wants to listen. I just think we're very well trained as scientists to be very stubborn. We have a position, this is our position, this is what we should do. And it can take a while to change people's opinions about that being the right way to do it, that being the right model that they should be using, right? It's not always a battle. I'm just exaggerating a little bit to make the point. All right. The actually other one I want to specifically talk to is also the perception of doing certain things. And I think this is maybe diminishing a little bit, but it's still around and people still talk about it. People worry, well, if I make a point to make my data structures flexible so that I can use different systems, I'm gonna lose performance. I'm gonna lose 10% of my performance. Oh my God, I can't do that. I can't lose 10% of my performance, even if it's not 10% or just some number, right? But consider other implications of that, right? Let's say you do implement a code with data structures that have some flexibility, so you can move from a multi-core system to an accelerator system to a completely different system in 3 years. If your data structure flexibility allows you to not have to go rewrite everything, maybe that 10% cost is really worth it, right? Because you might be paying 10% on the time to get the answer to your question when you're doing your simulation right now, but then you also don't have to take a pause and rewrite your code, right? And so there's this concept of the cost, right? People are often like, well, my time just went up when I ran my code, and they have a really instinctive response to that. Think about the long-term implications of making good choices with your application. Think about how this might help you, not just in this particular campaign, but over the course of the life of how you expect to be using this application. All right. And for the sake of time, I'm going to skip to the other point is I'm not trying to hide anything from you. These are sort of things I've touched on a little bit, but that scientific applications are not the same, right, as writing a piece of code for Microsoft and Google. And one of the things that's really quite different, really, is the lifecycle. And you can sort of look at this afterwards, and there can be some follow-up conversations. But for the most part, right, most people think about in terms of the life cycle of their application as they think about it from this very scientific perspective, right? And it makes complete sense, right? Because when you're thinking about what you need to do, you're thinking about whatever your question you have, the physical world. And you turn that into a model, right? You turn that into whatever equations will represent that. Then you discretize those in some way, shape, or form that you can actually calculate on a computer. You figure out solvers that can actually do that effectively. You implement them. You make sure 1 + 1 = 2. You run simulations, and you rinse, lather, repeat. Right? And that is a totally true process, right? That absolutely happens. But there's a lot more that goes into writing a scientific application. Probably the most pointed one, I will say, this is not the only one, is think about your workflow, right? One of the biggest transitions happening in large-scale computational science today is that we don't have people saying, I have a 2-week campaign I need to run on. We don't have everybody saying, I have a 2-week campaign I need to run to solve this scientific problem. I will generate 3 petabytes of data, and then I need to spend the next 2 months doing analysis on it to come up with my answer. Totally reasonable workflow. That is absolutely a workflow that exists. It used to be the absolutely dominant workflow. But that is not that does not dominate right now, in the sense that it is not the only workflow people are doing, and basically it's evenly spread between people who need to do huge parameter sweeps, who need to plow through soon almost an exabyte of data, right? And they need to be running millions of simulations, right? Maybe small, fast ones, but millions of simulations on that data to reduce that data set to something useful. Think about the workflow to run 1 million simulations. The workflow to do these things 10 years ago was a grad student. You were the workflow. And that's what you did, and hopefully, if you were smart about it, you wrote a script to help you manage it. And you tracked that as well as you could. But the scientific process includes that workflow. It does not just include, say, how you think about the physical world and turn that into the equations and make sure that the answer is right. The scientific process also involves tracking how you do all of the experiments, what experiments you're doing, being able to reproduce them so you know exactly what runs you did where, et cetera. And using tools to help you do that, because that should not, the more time you can save to actually move forward and not necessarily just be writing script after script after script to track this and hope that you can find the right thing in the directory is important. And so there's other aspects of this, but this is one I want to point out that make sure you're thinking about, right? Make sure you remember that the process of thinking about setting up, running, analysis, storing, going back, reproducibility is as much a part of your scientific process as thinking about getting a good code that gives you the right answer and the right problem, right? And should not be forgotten. All right. So really, in the end, a couple best practices for you to think about, right? That you can sort of go forward today thinking about, well, if I'm not implementing that, have I made a conscious decision why I'm not doing that? Can I implement it? Can I get help doing that? Whatever. An absolute baseline, sort of things that you really, really need to consider if you're not. The extensible code design means that what you've done is abstract things so that you are not locked in, right? You have some abstractions. You've got subroutines. You've got perhaps templates, whatever it may be, in whatever language you prefer to use, that allows you to dexterously build your code and expand the physics capabilities within it. There's a lot of different ways to do that. I mean, that's the sort of the topic of software architecture, but explore that a little bit. You don't have to become a software architecture expert, but there's a lot of really good basics that you can think about when you're writing a scientific application. Frankly, trust me, because I've done it. You can even do it in Fortran, old Fortran. You can do it. Every language will let you do it. Version control and automated testing will make your life easier. I'll leave it at that, because that will be covered later today. It will make your life a lot easier. And you can even do so much of it on your laptop, right? There's so much you can do that doesn't require that you have some complicated infrastructure. You could do a lot locally. The verification and validation, I think, is really absolutely crucial to make sure you trust what tool you're using. Remember, right? Imagine the LHC sort of running, right, and one of the big experiments just whoops, right? They completely screwed something up, right? They just designed it wrong. I'm not saying that's never happened, because it does, right? But when it does happen, it's normally big news, right? Big new magnets being designed and deployed, and everything's delayed. In the end, you're using a huge experimental facility, right, to do your work. You're using a supercomputer. Doesn't matter where it is probably an expensive big machine. You are using an expensive application to do it because your time is incredibly expensive. That's where most of our money goes to, is people, right? People time is expensive. Your time is valuable. So your application is valuable. So make sure it does the right thing. Make sure it tells you to when it should tell you to, all right? Define coding standards. These don't have to be complex or long. Just set up a few rules for yourself, right? So that if you are the sole programmer, that you can just consistently do those, and it will help you, because you will forget things. This goes with documentation as well. You will forget things because you're going to get older. I promise you. And your memory won't stay as good as you think it might be. So document it and use standards that will help you move forward. It'll also help you be faster in writing your application. And as I said, this is sort of really touching with the coding and testing standards. Well-defined policies, right? So what this means is does not mean you have to lock down the code. It does not mean that you have to have some complicated process for people who might want to contribute to your code and you have some huge review process, but just some process, right? If somebody wants to contribute, if you want to collaborate, if you have well-defined policies for maintaining the code, reviewing it every once in a while, checking it, releasing updates if you've got users, how they're distributed, right? So decide, right, if you want people to be able to hand your code around or if you want people to only download it, just little things like that. And documentation. It's small but huge, right? More people will use your code if you do this. If you're interested in developing a community of people, more people in your group, your research group will be able to use your code if you do this. I promise you that. And will contribute to it better if there's documentation. And globally, what will happen is that your code will live longer than you think it will, right? When you make that choice to write like, I just gotta get something done and I will fix it later, and you don't document it, that code will still be there in 5 years. I promise you, if that hasn't happened to you already, it will, right? And so documentation really helps people 5 years from now who are like going, what is that? Unwind what you've done and be able to test their science at that point much better. But again, this also helps you, right? This also helps you remind you what you've done. So some other things to really consider about this, right? The reproducibility and provenance, right? This will also be talked about today. But this is really this concept that you really need to make sure that your code gave an answer a year ago, and it can still give that answer. Or if it cannot give that answer, you know why it can't give that answer, right? Maybe you improved something, right? But that you understand, and you have some way to and you do have some way to reproduce it, right? Just consider if somebody says, you wrote this paper, I can't reproduce your results, right? For an experimentalist, right, this is a pretty crucial thing. That's the end of sort of those results. If somebody says, I can't reproduce your results, think about, again, your application and your simulation experiments in the same vein. You need to be able to reproduce them for good science. Lifecycle management is this concept that I was talking about, that you really want to think about, well, all right, I think this is only my project as a postdoc, but maybe this might live a little bit longer. Maybe there are choices I could make that'll make it easier for me to use the code in 5 years, whatever, right? Whatever you're thinking about in terms of the life cycle of your application, always try to add a little bit more to it because reality happens and your code will live longer. But really try to make decisions with that life cycle in mind if you can. And the one I'm not going to talk about in the introduction as much, although it's really important, is consider open development. Consider an open source software. Again, world so different today than it was 10 years ago. There's still a lot of people who write their scientific applications, and this is my code, you may not have it, but that's a lot less common. Open source software, especially open source software where people are able to contribute to it and engage in it, actually tends to build a lot more trust in the results because it's not somebody's code that they've got off in their lab, right? Oh, I know this application, right? Yeah, I know lamps, right? And I know this particular problem and how they configured it. I can understand that. That engenders trust, right? That people will believe your results and be more willing to engage. So consider that open source process. There are its own sociological challenges when you do that, right? Managing a community and managing people contributing to code. That's why some of these policies for contribution and maintenance are really important if you consider doing that. But it's incredibly valuable. It can engender a lot of trust for the work you've got going forward. All right. Any questions? I sort of plowed through it a little bit, but. All right. Yes?
Thank you, Katherine. I enjoyed that a lot. I wanted to share a few comments. Being from NASA, since you started with a couple of slides about NASA, I thought I should make a couple comments.
I mean, no offense, NASA. Just as a note, I tried to choose a broad variety of examples.
Yeah, so I want to completely echo everything you said and kind of comment a little bit. Give you a little context where I'm coming from. I've been on the large CFD development team for 25 years at NASA. Our software burns the most cycles at the agency every year. It's a big, major project. The senior aerotherm anatomist at NASA is part of our team. Literally, when the shuttle was on orbit, if a tile fell off, at launch, he would get a phone call literally in the middle of the night They clear everybody off the machines, and he has to determine if those 6 or 7 people can get home safely in a week. Okay, he's got a week to do that with a simulation code. So we've been doing a lot of these things for years and years, coding standards, performance testing, V&V, M&S, regression testing, compiling across 10 machines, every commit that comes in, unit testing, Scrum, pair programming. We did, a series of papers on this stuff 15 years ago. But my point is, and what we really, really struggle with, it doesn't come for free, and I think that came out in your talk. It comes potentially at a great cost. And to some degree, our science has suffered because of it, because where I think your agency is very fortunate is you have corporate buy-in into the fact that software is a product and there is value in recognizing it as part of the process of delivering science. We struggle to make that case. I can't tell you how often I go to management and say, you're funding a wind tunnel experiment with 10 technicians to keep the facility in order. Give me 10 technicians for my software to keep GitLab running and Jenkins and all the tools involved with doing all this. And so it's just a comment that our team struggles to keep that ball rolling. I mean, I have MIT PhDs in, applied numerical methods and so forth. All they do all day long is keep track of this automated 24/7 builds. I mean, there's always, a system upgrade somewhere that they come in the morning and something broke and they've got to fix it somewhere. So there is a cost to it, and we struggle with that. You've got to have FTEs allocated for that, for all this stuff.
And I do want to emphasize, while I was I think driving home a point, I think everybody struggles with it, right? So like even on the DOE side, there's certainly one part of it, right, that I think has experienced greater support for that historically. But on the open science side, right, I think in the end this is one of the things that has been most amazing is that there has been this at least transition, say, with the students at the summer school, right, over the course of the past 5 years, that people are thinking about it, where they weren't thinking about it 5 years ago. I think it's a very slow change.
Yeah, so I'm very eager to hear the rest of this. I'm very eager to talk to Mike in the breakouts about some of these issues.
Yeah. It is a really, this is a cultural change, right, without, I think, any doubt. And so I don't think anybody believes that a cultural change can really happen dramatically or quickly, right? This is a cultural change. And I think it's going now, it's going forward now. And to some degree, right, I think as scientists today who are sort of thinking about it, you're going to be pushing people pretty hard. And you're going to run into the resistance pretty substantially. I mean, this is one of the biggest issues actually for the leadership computing facilities. We run into this because we have projects coming in, right? We might get, as I said, 30 projects to use one of the biggest machines in the world who don't have code teams, right? And so the question of whether they have a software process to make sure that their code is doing the right thing, that's in the end where we often have to step in and help them too, because they don't have the people otherwise to help them do it. So I hear you. Yeah.
What's your favorite programming paradigm?
Programming language?
Programming paradigm.
Oh, that's an interesting question. So I will answer your question by not answering it. I generally can program, I think, well, at least I used to. I'm going to say this safely. I'm going to say I used to be able to program, and I really enjoyed programming almost sort of in any language for almost anything, right? In the sense that it's kind of fun to sort of have to think and frame a problem differently. So right now, I have enjoyed more sort of thinking about how, this is not quite the answer to your question, how you exploit as much parallelism in an application as possible. How you can get down and really exploit that and see what's in there. And that can be in anything, whether that's MPI and OpenMP or even CUDA or whatever. I'm not the biggest CUDA fan, right? And that's not, I realize, the answer to your question. But I think that's one of sort of the hidden questions that people don't often understand about their applications, is really how much parallelism they might have in there and what limits they have. So it's actually more of an application question, sort of what's more interesting to me about coding and applications and parallelism within it.
What's your favorite programming paradigm for reaching that flexibility you mentioned? That's why I asked your favorite.
Yeah, so separate, well, perhaps this is what you mean. So separation concerns is one of the biggest ones, right? So really having good abstractions right? So make sure that you have a data structure or data structures, flexibility in your data structures that allow you to consider asking questions slightly differently or use machines in slightly different ways. There's a variety of different solutions to do that today. Some people boil their own. There are libraries that are emerging that can help you do that. But even making sure that you have things like you identify in abstractions in your application where you have what might be node-level parallelism, right? And maybe those are routines, right? Maybe those are whatever hierarchy for whatever language you're using is represented in those. But this is the part where I think is most important, right? You need to have that flexibility in data structures. You need to have flexibility understanding, representing in the actual structure of your code what kind of parallelism you have. Like when you go down to, and I know I have to stop soon, I'm gonna get finished, but when you get down to the point where you're thinking about, well, this loop, right? This is the loop that I really have to optimize the heck out of, right? You don't want that loop to be duplicated 20 times, right? In different implementations, right? You want a nice flexible infrastructure and abstractions in your routines so that you can sort of say, well, I don't have to rewrite thousands of lines of code. I have to rewrite this 100, right, if I want to get really good performance on this particular machine. That's a more general answer, but yeah. Any other questions? Yeah.
You think it's important now to be able to manage complex software more than before because it's getting more complex or because it is more predictive than before?
Oh, I think it's probably a combination of both. I'm going to repeat the question to make sure I heard it right, which is that is the science actually getting more complex or is it getting more predictive, right? So is that what you're asking?
Computational part is more predictive than before, more critical or?
So I think it's a combination. We certainly see more people who are using it to be really predictive, right? Who are using it to design materials, for example, right? And therefore, they need a better answer, right, than they might have needed before, right, where it was just sort of coming up with an energy or something like that. And so we do see more people beginning to trust simulations so that they can use it to really be predictive for a particular application. That makes it more complex, right, though, in order to believe that, in order to trust that, you need to have better physics, right, that you can trust better, better numerics that you can trust better. And so I think it's coupled. But in some respect, there's absolutely science that is just getting more complex, right? You can't solve the problem unless you integrate a lot more multi-physics into the question. Yeah. All right.
Just make one quick comment.
Yeah.
It seems like so I really like this definition of technical debt so I haven't heard that before, but it's definitely there. But I think one thing that we don't consider, or that wasn't considered or maybe said, was that we also have scientific debt, which is on the same end of this, on a different end of this scale, which is kind of what I feel like Eric was referring to. And it's really about trying to thread this needle. And I feel like we need to have buy-in from people on our level, which is kind of what you're doing, trying to get us to get buy-in. But you also need buy-in from above. In the scientific community, this is, very difficult.
Yeah, and I agree, right? And this goes back to, without a doubt, you'll be hitting walls, right, at times where people don't want to hear it. That gets back to the listening skills and the people skills. I'm not joking, right? But like, it is to some degree a good laugh. I think more people are buying into it. And there's been actually, in the end, the biggest limit is that there's beginning to be money behind it, right? And in the end, the more senior people who might not be listening are more likely to listen when there's money behind it. And that's actually a shift that has happened. Not completely, not everywhere, but it helps. And I think it also helps, there are people who it kind of takes like that nth postdoc who sort of says, no, this is important. And so it just requires perseverance. I hate to say it, right? But I would say there's very little other option but perseverance.